All right, thank you very much for the invitation. I've seen many familiar names. Happy to meet you virtually. And I'm not going to talk very mathematical today, so I've provided a link to a draft of a half-ready book that has a lot of mathematics in it for math lovers. But today I'd like to raise a couple of questions on how the field could and should be developing in the future according to my point of view. Maybe you disagree, but at least we should discuss those points. So, of course, with big data and artificial intelligence, we are heading towards smart cities and smart nations. And the question is really, how should we go about it? What are the implications of those technologies? And how do we want to build this future digital society? I start with some stuff that is probably familiar to some of you. So what interests me in traffic is that there's a lot of complex behavior in this simulation. For example, we have a freeway with an on-ramp, and you can see that there is a stable traffic flow for some time until we reduce the density temporarily. And that perturbation actually propagates forward together with the vehicles. But at some point in time, actually, after this perturbation has already passed the location of the on-ramp, we see a boomerang effect. The perturbation has grown large, it turns around and it arrives again at the location of the bottleneck and causes a capacity drop, a breakdown of traffic flow, even though the inflow is the same. And then a big traffic jam evolves, and there's actually also oscillatory traffic flow in that area. So this simulation already summarizes a lot of particular features of traffic flows, including metastability and history dependence, and so on and so on. And the question that we had a couple of years ago is, could we ever understand the complexity of real complex traffic flow, which is even more complex than this? And what we eventually did is we came up with elementary congestion patterns and tried to understand more complex congestion patterns based on those elementary patterns. So what you see over here is a collection of different congested traffic states that have been produced by a traffic model. You can do that both with macroscopic and microscopic traffic models if you use the right kinds of models, and you're very familiar with this. And of course, in the meantime, there are hundreds of different models with strengths and weaknesses. And the question is, how should we classify those models? And one way of doing this is through so-called phase diagrams that summarize, in a sense, the different kinds of free and congested flows that can occur, and what are the conditions under which these different patterns occur. So what you see here can actually be understood theoretically. So in a sense, it's a prediction about real behavior of empirical traffic flows. And then the question is, of course, how well does that actually represent what is going on in the real world? And in fact, according to my point of view, it actually fits empirical findings quite well. These are findings for German freeways over here. Of course, things could be slightly different in other countries because parameters might be different. But altogether, my personal summary of the state of affairs is that we understand traffic flows and traffic congestion quite well to a point where we can actually calculate the extension of traffic congestion and also the delay times in advance once traffic flow has broken down. So the other nice thing is that I believe it's possible to derive an analytical theory of traffic flow that allows us to understand those different congestion patterns and their features and much more. And that is something that couldn't be expected from the very beginning, given the complexity of traffic flows. And I think that's actually quite interesting. Another interesting point is that these insights can also be used for new kinds of freeway traffic control. And so what we did a couple of years back, I think people have not been even talking about Google self-driving cars at that time. We've been looking into future cars, which are of course now available, that would have sensors allowing for perception, inter-vehicle communication, and cooperative determination of traffic states, something like cognition, decision making, and so on and so on. And now the point is that our approach didn't foresee that we would build a giant traffic control center that would collect all data of all vehicles and then control all cars in a brute force way through the centralized control center, but we would actually modify the interactions through technology in such a way that a different outcome would result as a outcome of self-organization. What you see here is a movie that shows stop and go traffic, as it's still common in most countries. And this is basically to show that those mathematical models we're using are capable of reproducing this very familiar phenomenon. And of course, it's very annoying. So that's the kind of self-organization that we wouldn't like to see, which is unintentional and produces this congestion that we'd like to get rid of. Now let's see what is the reason for this. Actually, there's an on-ramp where a few cars are trying to sneak in the freeway. That produces small disruptions. Those are being amplified because of the instability of traffic flow under those conditions, causes stop and go traffic. Now assume that we would equip a certain share of these cars with radar sensors that measure distances and relative velocities and would actually allow these cars to accelerate and decelerate automatically in a slightly different way from what real drivers do. And as you can see, this allows us to dissolve the traffic jams, even though there's now the same inflow through the freeway and the on-ramp. There was free traffic flow in the end. And actually, this works even if not all vehicles are equipped with that kind of technology. What we've shown in our simulation scenarios is that the equipment rate of 30 to 40% would already have potentially dramatic positive impacts on the overall traffic flow. So what we are doing is we are using the Internet of Things in a sense to create real-time feedback and change the interaction between neighboring cars in such a way that the outcome of self-organization would be different and favorable. That means traffic flow would be stabilized and the capacity of the flow would be slightly increased, so we could actually dissolve the traffic jam. So basically what we're seeing here is that with the Internet of Things, we can make self-organization work 300 years after Adam Smith's idea of the invisible hand. Now the question is, how powerful is this approach overall? And let's move on to the next challenge, which is basically urban traffic flow. Of course, there are noble goals of traffic planning, better mobility, less pollution, less noise, less traffic. But this is often the reality. And we often see urban gridlock. So now the question is how to fix this. And some people have suggested that now with big data and artificial intelligence, we can get rid of this and are proposing kind of a brute force approach. So without any doubt, we're now living in an age of big data where within just 60 seconds, 170 million emails are being sent, hundreds of thousands of Facebook posts, where we query Google hundreds of thousands of times. And as we move around, as we go shopping, more and more data is added to this heap of big data, which is then being fed into artificial intelligence in order to help us organize our life in our societies in many areas, including traffic flow and mobility. And of course, we're now talking about smart cities where artificial intelligence is, of course, an opportunity. I don't deny that at all. And we'll be using it in order to improve logistics also in multimodal and hybrid transportation situations. And of course, you're aware of autonomous cars. And what we now need to do is we need to simulate automated traffic flow and mixed traffic. It's clear. And multimodal traffic, and adding also logistical challenges, and not only efficiency in terms of travel times and fuel consumption, but more importantly, sustainability. If we really want to reduce CO2 emissions dramatically, then a lot has to change in the way we organize traffic flows on freeways, and even more so in cities. Maybe the entire organization of cities has to change, not only that of cars. Some people have then started to ask, could cities be run like giant machines, with the Internet of Things and new kinds of information transmission, like Wi-Fi, LED-based communication, and then quantum computers that would basically process all this information. Google says 100 million times faster than a PC. What could we do with such a thing? Some people have asked, and is it the approach that we should take? Because actually, quite a few people have become nervous about this vision of the future, which is based on mass surveillance and centralized control. So some people see it as a dystopian future and actually rebel against such plans, and not only in Toronto. The other question is, how well is that working? And there are a lot of question marks and doubts and criticisms. And if you look at the most livable cities in the world, then surprisingly, you don't find those cities where you would expect the largest degree of digitization. So somehow, perhaps we're going about it in the wrong way, because cities are not just giant supply chains and logistics systems. They're also not just giant entertainment parks where people consume pre-manufactured experiences. Cities are places where we make friends, where we meet other people, where we are creative and innovative and explore life and so on. So it's not something that we can fully automate. And besides this, there is trouble because even though processing power is increasing quickly, it seems that data volume is increasing even faster than that, so that there is a growing share of dark data that would never be processed potentially. And we would need to know what share of the data to process in what way. So science is needed here. Plus, there is an explosion of systemic complexity as we go on networking the world. So maybe even the data volume is not catching up with this challenge, such that surprisingly, even though we have more data than ever and better technology than ever, we're losing control of the world as we're trying to control it in a top-down way. And we need a new control paradigm called distributed control. Because in a highly networked world, whatever you do has an impact on others. So they're not just intended effects, but they're side effects, they're feedback effects, and they're cascading effects. And as a result, complex systems such as traffic flow or our society or markets cannot be steered like a car. And you know very well those phenomena based on systemic instability, such as phantom traffic jams, as people call them. And there are many other problems that are also based on systemic instability, where basically we find systemic outcomes that nobody wanted to happen. And then the question is, how do we go about this? And it turns out that in many cases, there are domino and cascading effects, and we need to interrupt them. So we need a particular design and organization. We need breaking points. And if we want to live in a more sustainable world, or maybe I should put it differently, given the sustainability challenges of the world, we can expect to face a number of crises and disasters in the future. And in order to prepare for this, we should build a resilient society that can handle those challenges flexibly and adapt to them and recover quickly and maybe even grow better than they were before in the sense of anti-fragilities. The question is how to get there. How would we need to organize our societies or the world in such a way to make it more resilient? And in fact, there are a number of factors that contribute to resilience, such as redundancy, diversity, decentralization, distributed control, subsidiarity, modular design, participatory resilience, solidarity, digital assistance, and self-organization. And from that point of view, we can say that cities and regions are actually relevant organizational units for a resilient society. So maybe we shouldn't try to control the entire world from one centralized control center, but maybe we should pursue a new paradigm that goes from top-down power and control to empowerment and coordination. That means go away from systems that are regulated and controlled, such as this one, quite familiar, I guess, for you, towards systems that work like this, which support the self-organization of the system in a way that is favorable and desirable. And I often like to show this video over here because it's kind of funny how well self-organization can work if you have a suitable design. Why does it work so well over here? Well, this is because you have unidirectional flow in the front, you have the opposite unidirectional flow in the back, and in between there is a buffer that allows everyone to adjust the speed such that you would find a gap in the traffic flow to cross it. Now, can we learn something from this example? And in fact, this was our approach. We wanted to have a new kind of traffic light control, which is adaptive to irregular street networks, to accidents, to building sites, to special events. And so what we did is that we came up with a new approach where traffic flows were actually controlling the traffic lights rather than the other way around. The question, of course, is how efficient would that be? So let us compare three ways of traffic light control. The left one in red shows the traffic control center, which collects as much data as possible and tries to come up with an optimal plan, which is then imposed on the entire city. It's like a benevolent dictator deciding for everyone what is the right thing to do. Then the control in the middle is based on local self-organization. The intersection would basically adjust the traffic lights to the incoming traffic flow at the neighboring intersection in such a way that the travel time would be minimized. That can be strictly solved, this problem, but there wouldn't be any coordination between neighboring intersections. In a sense, each intersection would behave like Homo economicus and trying to locally optimize the behavior, not taking care of anybody else, right? So we would probably expect that this can't be performing as well as the centralized control. And then there's the one on the right where we do the same thing, but if there is a long vehicle queue, then we would first clear the vehicle queue before we go back to travel time minimization. So basically, this is behaving nicely towards neighboring intersections by trying to avoid spillover effects. So we would think the travel time minimization in the middle would be better than the friendly control on the right, and the best would be the centralized traffic light control. Now, what we have implemented was very much inspired actually by the oscillatory flows in pedestrian crowds that we found at bottlenecks. And this can be understood based on a pressure principle. So the idea was that we could have a generalized pressure principle self-organize oscillatory flows at intersections and thereby define a traffic light control. So the traffic flows would indeed control the traffic lights, and we would have a short-term anticipation as we would measure the inflows, not just the outflows from road sections. And that would be considered in the way the traffic lights behave. As you can see on the top right, we'll find beautiful green waves that self-organize. The question is, how well would it work if we don't have such a regular square network as, for example, in Manhattan or Barcelona? And we'll come back to this, okay? For the time being, let's focus on a single intersection. And here the red curve actually shows what happens for this centralized traffic light control. As we increase the capacity utilization of the intersection, the vehicle queue increases. That's an expected effect, okay? Nothing special here. But let's see how this selfish self-organization based on a Homo economicus principle works. Actually, for small capacity utilization, it comes with much smaller queue lengths. However, around 0.6 capacity utilization, you see the queue lengths explode. So basically, the beautiful self-organization breaks down and you will get a monster traffic jam. So from there on, the centralized traffic control performs much better. And that's why we have, of course, those control centers, right? But surprisingly, yeah, so basically we can say for large capacity utilization, Adam Smith's invisible hand fails. But surprisingly, the other regarding friendly local traffic light control is performing better all the way. Okay, so we can make the invisible hand work, and we can come up with bottom-up self-organization that outsmarts apparently optimal top-down control. Why am I saying apparently optimal? Because you cannot strictly optimize in real time because of the complexity of the optimization problem. So the centralized control will make simplifications. Now let's see how well that actually worked. So at that time, we talked to the city authorities in Dresden, Germany, and they said, we're happy with our traffic light control apart from one area, and there you can show how smart you are. over here, we're in the center of Dresden. And you see a very irregular road network. And moreover, there are a lot of trams and buses actually cutting through. And they wanted to prioritize public transport, which they couldn't do because it would destroy the green waves that would be produced by their state-of-the-art traffic control that they bought for, I think, several million euros or so. It turns out, however, that our self-organized traffic light control came up with a different kind of green wave that was more flexible and basically using random gaps in the traffic flow in order to coordinate traffic activities. And we could do it in such a way that we could actually benefit public transport a lot. That means prioritize public transport to some extent, at least, without harming motorized traffic flow. So in the end, we had improvements for all traffic participants, and by the way, for the environment as well. So this is interesting. It's now being tested in other cities as well. And the question is, can we use that approach also to solve other problems, such as the sustainability problem? And so we have basically thought about the question, how can we actually use self-organization principles to solve the sustainability problem of the world? How could we build a socio-ecological finance system? Because at the moment, every one of us is throwing away about 50 tons of waste in a lifetime. And this includes a lot of valuable reusable materials such as tables, furniture, cars, computers, smartphones, and so on. And one of the problems why we have this sustainability issues, which are really a matter of life and death eventually, is that we have typically supply chains rather than a circular economy where we would reuse resources. And the question is how to get there. Regulation hasn't brought us very far in the past decades. But now there is the Internet of Things. And with that Internet of Things, we can do all sorts of measurements. We can build a measurement network. Our proposal is to build a public one that everyone can use and contribute to and participate in. And we could use it to map noise and CO2 and poisons and other externalities such as reusable waste and good things such as environmental qualities and education, health, and so on and so on. And so there would be many externalities that would be separately measured. And for each of them, we would come up with a new kind of currency to create a feedback and incentive systems, a multidimensional incentive system that increases positive externalities and reduces negative ones. Otherwise, takes care of fair compensation. And such a system can now be built. So we have been working on combining the Internet of Things with blockchain technology in order to create incentives and real-time feedbacks that would potentially, in perspective, add forces in our economic systems that would work towards closing logistic cycles and thereby create the co-evolution of the system towards a circular economy and sharing economy. That's the idea. So now this is very different from what economists tend to do today, where they try to optimize a system. And optimization uses a one-dimensional goal function because you want to make greater, smaller operations, right? But as you do this, basically, you have to map the complexity of the world on one dimension. So basically, you know, a city actually has many different purposes and goals. So among them, health, education, finance, economic prosperity, and so on and so on. So that basically is part of each city But then, for whatever reason, we map everything on one-dimensional function, some utility function, maybe money. And that, of course, oversimplifies the complexity of the problem. And there's so many goals, such as prosperity, sustainability, health, education, culture, and so on. But optimization neglects all goals but one. That cannot be good for the system, we believe, and that's why we're proposing to build a multidimensional finance system, a socio-ecological finance system that combines measurements of the environment with these new incentives. And we think that is actually a totally new paradigm. This multidimensional value exchange system provides many more possibilities to find solutions that benefit all. The space of possible solutions is significantly increased. And by the way, nature seems to work according to such an approach. So, for example, take the human body, which is largely a self-organizing system, but a system that is not being controlled by one variable, not even fully controlled by the brain. There's a lot of self-organization going on, and there are many feedback cycles that are separate, that are not controlled by one single variable, such as money. And as a result, the typical supply networks in our economy look very different actually from metabolic networks that contain circles and feedback loops and so on. So there's a big difference. But importantly, nature has learned to be a circular economy. It's basically reusing all resources, and it's very efficient in that. So we could probably learn a lot from the organization of logistic systems in nature if we want to build a sustainable economy, a sharing and circular economy. And by the way, what seems to be important is that there is a lot of symbiosis happening also in this ecological systems that I'm showing you over here. So I propose to come up with bio-inspired solutions for our logistics system, for our economy, for our society. And I'd like to move on talking about social self-organization, which actually can be quite efficient, as Nobel Prize winner Elinor Ostrom has shown, if we just apply proper design principles. And she was interested in public goods problems where you would often find tragedies of the commons, but she came up with 8 principles that would allow to overcome those tragedies of the commons based on local self-organization, self-regulation. And she proposed a multi-hierarchical approach to solve global issues. In fact, there are a number of decentralized mechanisms to promote cooperation and social order and to overcome tragedies of the commons. There's dozens of such mechanisms, I would say, as has been shown in evolutionary biology and game theory, and many mathematicians have also contributed to this field. Among these mechanisms are direct reciprocity based on repeated interactions, or reputation systems based on indirect interactions, but also, for example, network thinking as it would emerge under certain kind of conditions, as we've shown it in this paper over here. So what we did just shortly was to simulate whether or not Homo economicus would actually be a natural outcome of human evolution. And the result was yes, but Homo economicus would result in a large area of the parameter space, but not when offspring are raised next to their neighbor, to their parents. But this is what humans do, actually, right? And that can make all the difference. So as a result, over many generations, we expect other regarding preferences, fairness preferences, actually to be developed. So people would develop social other regarding features, and they would develop network thinking and conditional cooperation. Also cooperation with strangers. And so basically there is a mechanism that could end up in world peace if we just are patient enough. And the question is, can these mechanisms be used and accelerated and supported by digital technology? And talking about network thinking, I would like to move on to collective intelligence, right? So many people have been fascinated by swarm behavior and have been talking about swarm intelligence. And of course, there are also books about the wisdom of crowds. There's also a book on the madness of crowds, I must admit. And so the question is, when do we find a wisdom of crowds and when do we find a madness of crowds? And that's a very active, interesting research field, both theoretical and empirical or experimental. And the question here is how to bring the best ideas of many minds together. And actually, what has been proposed is that there would be different phases in which we proceed. In the first phase, people would collect different points of view and different arguments that would matter for the solution of a complex problem. And those arguments would be structured in such an argument graph, and different perspectives would be worked out that would have to be considered in order to get a good picture of the problem. So it would really be important to combine different perspectives, and it's important to have a diverse approach or diverse group with different approaches, different points of view, because this is actually what produces better solutions. So it's diversity that wins in a sense. And it's also possible to come up with incentive mechanisms that would actually support such diverse feedbacks that could provide a better judgment of the problem and also better solutions, as we've shown in this BNES paper. So altogether, there would be 4 phases to produce this collective intelligence. First of all, there would be a phase of independent exploration. Here, people should not be manipulated in their search for information and possible solutions. In phase 2, then people would talk to each other. There would be information exchange. In phase 3, representatives of different perspectives would sit together at a round table to work out integrated solutions through deliberative processes and innovative approaches. And then only finally, the people would vote among those integrated solutions that would try to match as many expectations and interests of people as possible. So there would be solutions that would work for many people. So in contrast to what we have today, which is kind of majority decisions that then impose those decisions on everyone, here it would be about trying to find all the different variables that matter and come up with integrated solutions that work for many. So it would actually be not that competitive as the way we are doing decision making today, and we would come up with better decisions. So heading towards my concluding part, even given big data and artificial intelligence, there are control problems that cannot be solved in real time because of their complexity. In particular, decentralized control approaches may perform better in complex systems with heterogeneous elements, large degree of fluctuations, short-term predictability. And this is because of the greater flexibility to local conditions and needs, and also greater robustness to perturbations, which delivers also some degrees of freedom, which can be highly desirable. So coming back to this distributed approach, the question is, how can we actually implement that on a global scale? And here the idea is that we would make competitions for better solutions among cities and regions around the world. So there would be different disciplines such as improving energy efficiency, reducing climate change, increasing resilience, or also sustainability, and any other discipline that may be of interest, okay? And so basically all stakeholders of a city, including the civil society and its citizens, would actually compete for improved solutions, and I, of course, would want to win compared to, say, the neighboring cities, or kind of New York City versus Tokyo versus London, and so on. But then, after, everyone has made an effort to improve the implementation and the solutions in the city, there would be also a cooperative phase, because the solutions worked out would be open source and Creative Commons. That means every city could take any solution developed in any of those cities, and companies could take those solutions as well and develop them further, combine them with each other, and this is how collective intelligence would actually come about, based on the best ideas around the entire world. So such a system would actually combine the best features of many systems, like competition as we know it from capitalism, collective intelligence as it should be in the center of democracy, experimentation, selection, which are basis of evolution, culture, and intelligent design as we can actually promote it with artificial intelligence. And we have actually come up with a test run. It was called Climate City Cup. Last year, there were different disciplines on how to improve basically environmental friendly behavior. We've been hacking for climate. We've been coming up with hackathons and summer schools, combining blockchain and Internet of Things. And you can see actually a lot of students who were really excited about developing solution approaches that would improve systems by real-time feedbacks based on measurements. And here you can see, for example, our efforts to develop an air quality sensor ourselves based on, the Fab Lab approach, and pretty much an open source approach, community-based. So these are the measurement sensors, and there's of course also some intelligent control unit, and then of course that data would be collected in an app, and would be used to compare the progress made in different cities, and so on and so on. So this approach would set itself apart from globalization. I'd like to call it localization because it is based on thinking global, but on acting local and diverse and making experiments and then learning from each other and helping each other. This kind of thinking, of course, is being spread quickly through open data and open innovation approaches, and that also reaches now the city level. In particular,
we just have a few more minutes for questions, so just to let you know.
Okay, thank you. I'm almost finished.
Okay, no problem.
So open source urbanism is exactly taking this route, which is inspired by Wikipedia and GitHub and Creative Commons, and moves towards open source architecture and open source spaces, open source hardware, based on openness, collaboration, modularity, granularity, and low-cost integration, and allows basically civil society to contribute to change and improvement. And that could matter not only for refugee camps and disaster-struck regions of the world, it could also contributing to making our local city quarters more livable, more colorful, more natural, more ecological, and so on. So the important point is here, not everything can be done in a top-down way. It's really important to bring in the bottom-up component and mobilize civil society and its power, the power of the ideas of many people, allowing them to bring in their skills, to engage in order to make a contribution to our future and our cities. And in fact, that very much corresponds to the experiences made in New York City. I recommend you to read this book by Alexander Washburn, The Nature of Urban Design, where he says, I could not control anything, but I could influence everything. And actually that graphic over here is from that book. So basically I'm concluding by saying, yes, we need to bring together cybernetics and synergy, but should it be a control center as in cybersyn? I don't think so. I believe synergetics is the way that really builds on empowering people and helping to coordinate activities through real-time feedback. And so success principles of a complex world would be co-learning, co-creation, coordination, cooperation, co-evolution, and actually collective intelligence. So we would have to go away from smart cities as just technology-driven entities that are kind of increasingly or even fully automatic towards cities that allow for citizen co-creation, that would build for people and for human values. And so designing for values is something that we need to learn. So we need to build in our constitutional and cultural values, and perhaps also personal values, into digital platforms to support the achievement of those goals. So we could learn to design for democracy, and let us build, therefore, digital democracy based on those principles and ideas. That means democracy by design. Thank you very much for your interest.